I will be explaining important university questions in the first unit of measure and integration. Okay, so let me start with from last to first. Okay, so here you can see Borel Cantelli Lemma at the end of the first unit. So here let us start studying from Borel Cantelli Lemma. You can see this it's a named lemma, no? So they may ask you, as you all know, they may ask you state and prove Borel Cantelli Lemma. So we have to be ready with the statement also. Okay. So here you can see the statement. Let's follow my notes. The Borel Cantelli Lemma. Here is the statement. Let k equal to 1 to infinitive is a countable collection of you are starting with let. So here you should not use let this is the countable collection. That is wrong. Let this be the countable collection of measurable sets. Okay. This is the common mistake. Most of them commit this mistake. That is why I am saying. If you are putting let means here you have to put be. Let this be. Okay. This is a countable collection of measurable sets. It means this is a collection of measurable sets. That is E1, E2, E3, E4 till E infinitive. They are what? They are measurable sets. For which a condition is given that summation k is equal to 1 to infinitive m of ek less than infinitive. It means when you find the measure of these measurable sets, okay, and also after finding that you will find the sum of that measures. So that will be less than infinitive. It means the sum of measure of measurable sets will be less than infinitive. Is that clear? Then what you have to prove is almost all x belongs to capital R. Okay, x is an element from capital R, belongs to at most finitely many of the EKs. It means you have to prove this x belongs to finitely many number of EKs. That is, x belongs to finite number of EKs. That is what you have to prove. It is not in the infinite number of EKs. X belongs to finite number of EKs. That is what you have to prove. Okay. So I hope you can understand this statement. First you have to take a collection. That is ek k equal to 1 to infinitive. It is a countable collection of measurable sets. And a condition you have to write. The condition is that summation k is equal to 1 to infinitive. Measure of ek less than infinitive. It means this value will be less than finite. Okay. Then all x belongs to R belongs to at most finite number, finitely many of the EKs. It means it belongs to finite number of EKs. That is what we have to prove. What belongs to finite number of EKs? This x. Okay. Let's start learning the proof. Proof by the countable subadditivity of m. It means you are having a proposition. You are using that proposition here. Okay. That is countable subadditivity of m is the name of that proposition. So we have from that proposition we have measure of union k equal to n to infinitive ek less than or equal to, this can be written like this. That is what our proposition. Okay, what proposition? Countable subadditivity of m. So measure of this less than or equal to union is becoming summation and you are bringing m inside the summation. So this will be changed like this by the countable subadditivity of m proposition. Now this value will be less than infinitive. That is, you are having that in the statement. For each n, it means in the statement you are having 1, k is equal to 1 to infinitive, but you are having k is equal to n to infinitive. You should not get confused. Here you are written for each n. It means you can look at this like k equal to 1 to infinitive also. For each n, it means n takes different values. When n equal to 1, n equal to 2, n equal to 2, n equal to 3, n equal to 4. Okay, for all the values you are getting. So it means for each n, no? So that is why you are applying this here. That is what in simple I can say like that. So here you are putting less than infinitive from the statement. So keep that, you will use it, okay, in the further steps. That is why keep that. Now by the continuity of measure, this is also a proposition. From that proposition you are writing this measure of intersection n equal to 1 to infinitive union k equal, that is this value, union k equal to n to infinitive ek is equal to limit n tends to infinitive measure of this value. Okay, measure of intersection n is equal to 1 to infinitive. Now in the bracket you have to write this, that is equal to limit n tends to infinitive measure of again this value. Okay, you are writing this from the proposition. The name of the proposition is continuity of measure. Now what you are going to do is, in the place of this you will substitute this value in the next step. Okay, I will show you. At that time it will become less than or equal to, because the value of this is less than or equal to this, no? So that is why when substituting the value for this in the next step you are getting less than or equal to. So here you will put less than or equal to limit n tends to infinitive this value. Now here look at this, n tends to infinitive. It means here you substitute n tends to infinitive, no? So here is also infinitive and this is also infinitive. So k is equal to infinity to infinitive. It means what? You will get infinity to infinity means you will get 0. When you find the measure you will get 0. So that is why you are putting 0. So measure of, you are getting measure of this, right, equal to 0. You are getting measure what? 0. So that is why you are saying x belongs to R is not belongs to this. Okay, what is this? This, okay, because you are getting measure of this, you are getting 0. So that is why x is not belongs to here. That is what you are writing. X belongs to, almost x belongs to or fail to belongs to this. Therefore x belongs to at most finitely many of the EKs. So that is why x is not belongs to infinite number of EKs. X belongs to what? At most finitely many of the EKs. That is how you are concluding the proof of this theorem.